Welcome back once again. So we want to take questions on moment forces and equilibrium of forces. Now, this is what I want you to do. Okay, I want you to study question study the slide for moment forces and equilibrium of forces. Okay, then I want you to go to top end chapter 6 and study, because there are questions you need understanding of these two topics 4 and 6. Yes, the truth is chapter 4 and 6 happens to be interwoven. Yes, those two topics are between each other. I mean, they have similar things in common. So there are times that from this topic I may enter that topic, from that topic I may enter this topic. Do you understand that? So I need you to go back. Not to go back, but go forward in quotes now. Then study that so that you can have a better understanding of this. Is that fine? Good. So let's move on to the question. Now, a nail is pulled from a wall. So let's have the wall. This is the wall. Okay. Then you have the nail. A nail is pulled from a wall with a string tied to the nail. Okay. If the string is inclined at 30 to the wall, okay, this is it, 30 to the wall. Yes, because for you to pull the nail, is that the nail, let's say something like the nail is there and I have to pull the nail like this. So let's have the boy that is pulling it down. Can you see? This boy is doing work. Yes, that's good. That's good. So now, after that, and the tension is what? 50 Newton. Calculate the effective force used in pulling the nail. The effective force used in pulling the nail. That means that we want to know in the recent, what is the amount of force that will pull the nail out, because the truth is pulled, you want to pull it from a wall, and of course the force that will pull out the effective force, will it actually be the horizontal or the vertical component of this tension? This is what I'm saying. If I want to remove something like this, yes, I'll pull it vertically out. Okay, but because the nail happens to be higher than the person, so it has to be pulled like this. But in the real sense, what you want to achieve is to pull it out. So the effective force is actually the force that will bring it out like this. Effective force, which is the horizontal component of the tension. Horizontal component of the what? Tension. And for me to get the horizontal component of the tension, now, I've always explained this almost every time I'm opportune to teach, especially when it is frictional forces, equilibrium of forces, that resolution is not dependent on, you need the understanding of the concept. It's not dependent on whether the angle is let's say leaning at the vertical, and it always has to be at the vertical. No, this is what I'm trying to say. Whenever you see a question that has an angle in it, the first thing you look for is, where is the position of the angle? You know, the angle can be here, the angle can be here, the angle can be here, the angle can be here. When it is here, that determines whether it will be sine or cos or tan that you use. When it is here, things changes. So a very good example is this. Now look at this. This is the position of the angle. So this place now is the adjacent. Do you agree with me? Now this place, which is the same thing as this place, is the what? is the opposite. My ability to distinguish which one is adjacent and which one is opposite gives me the answer to this question. So in this case now, I have 30 degree 50, right? So this is the angle. This is the tension. Where is the adjacent? This is the adjacent, opposite, opposite, hypotenuse, hypotenuse, opposite, hypotenuse, opposite. That's so. So that means that I'll use sine. That is for me to get effective force. That will be T sine theta. Now, the game changes if the angle is here and not here. If the angle is here, this place, which was my opposite, will now be adjacent, no longer opposite, but adjacent. No longer opposite, but what? Adjacent. And once this place is adjacent, you know the meaning of that? It simply means that this other side or this side will now be no longer opposite. I mean, no longer adjacent, but opposite. Do you understand? Do you understand? Well, we'll still have a good deal with this kind of, there are still more. So that means that for me to get this, I will just do, all I need to do is 50 sine 30, which is 25 Newton. Now, if I were looking for Ty now, that is this component, let's say this is the effective one. That's an assumption. It should have been Ty. Yes, and if it is Ty, that will be T cos theta. So far the angle is here. You don't need, anytime you see the angle, the position of the angle, look for which one is adjacent, look for which side is opposite. So from that determines whether you use adjacent, you use so, or you use ka. Yes, and or toa. Toa, yes, you always use toa once it is adjacent and opposite. Of course, it will also change. Do you understand that? Very good. Let's look at this other example. Now you can see that this question is dealing with both resolution of forces and also dealing with equilibrium of forces. Yes, subsequent class or subsequent video, we are going to look at questions of moment, but stay keen to me as I continue this. Now, the next thing is we have a particle is maintained in equilibrium under the system of forces shown in the diagram. Calculate W and calculate theta. Now, a question like this, you must be able to resolve what you have to what? To right angle triangle. Now, I want you to note that this topic specifically, quite a lot of students have issue with this topic. Yes, quite a lot of students. And these are common questions in WAEC, in JAMB, if you mention SAT, in whichever exam. In physics, these are basic and common questions. Questions like, topics. I told you that topics like motion, topics like force dynamics, that's forces, frictional force, they are topics that people find difficult comprehending, which is not actually difficult. All you just need to do is to understand the concepts. So let's go ahead. Now, I have this. I'm going to bring this to right angle triangle. This, the rope in quotes now. In quotes is 10. But you have two other forces is used to balance up. That is, these other two forces, this 10 balances up these other two forces. Good. Now, okay, let me do this. Let me go ahead and do this. Let me bring the triangle here instead. Good. Now, that means that this one, okay, I can bring it here. So I can put 5n here. Do you agree with me? Of course, it's possible. Okay, the direction of this one will be like this, right? Good. Now, this one, W, will now be what? I can also bring it here like this. Coming down, W. Exactly. This picture that you have here shows that this body is at equilibrium. How do I know? You can see the direction of the 3. You see it's going like this, then goes up, then come down, such that you have a closed triangle, something like this. Then from here to here, then this is a closed triangle. And summation of all the forces is equals to 0 in a diagram like this. Now, there are moments when you may have something like this. This is different from this. In this one, F1, F2, F3. In this one is at equilibrium. How? Because it's a closed triangle. The summation of all the forces will give you 0. And you can see that is indicated by the direction of the arrow. None of the arrow is coming to meet. Now, in the case of this, you can see that it's moved like this. Then, okay, no. Let me put it. Yes, good, very good. See, it moved like this, then like this. Now, in the case of this one, this is the resultant. This is the result. This is usually used in the case of vector quantity. Yes, where, for instance, you have a boy move this distance, then moves up, then you now ask what is the resultant. Okay, but when you have case of equilibrium, where summation of all the forces equals to 0, this is the type of triangle you have. Is that clear? So let's go ahead and solve this question.